Hi everyone. Today I'll talk about how to efficiently execute cross-shard transaction in sharded blockchain. And this is a joint work with Vinit Krishnan and Lingren, and we all are from UIUC. So in this camp, I think everybody knows what blockchains are. So even then, a brief summary: we have a network of nodes, some which could be Byzantine, marked here in red, and they maintain a globally replicated state. They run a consensus algorithm to create new blocks and append it to the chain and update the state. Important thing to note here is that in earlier designs, we had a global replication, and that resulted into scalability issues, and primarily due to the fact that each node used to maintain their entire state. Everyone participated in single consensus, and everybody processed all the transactions. And this resulted in scalability issues. And one of the promising solutions is sharding. And the idea in sharding is as follows. So instead of running a single consensus across the whole network, we divide the nodes into smaller groups. Each group is called a shard. Here we have three shards: the orange, green, and the gray shard. Each shard maintains their own blockchain, and clients send transactions to respective shard, and only those shards include these transactions in their block and update the local state. The other shards, which are not involved in these transactions, mostly remain oblivious to the things that are happening in remaining shards. So the question is like, are you done with the scalability problem? And the answer is no, because sharding usually has reduced fault tolerance, because now you have to ensure that adversity do not control threshold number of nodes in each shard. And we also have to address the problem of cross-shard transactions. And in this talk, I'll primarily focus on the later problem. So what are cross-shard transactions? In very brief, cross-shard transactions are transactions that require attention of more than one shard. For example, here we have three shards: orange, green, and gray. And let's say a green user here has a bank account in an orange shard. So whenever she wants to send a transaction, the transaction should be handled by both green and orange shard. So if we have an orange user and wants to interact with contracts stored in multiple shards, let's say gray and the green, then all the three shards should come together to execute such cross-shard transactions. And it's important to note here that cross-shard transactions are essential in a sharded system. Otherwise, it will be equivalent to running, say, an independent parallel blockchains. So currently, in almost all systems, cross-shard transactions are handled using what is called two-phase commit. So this is a classic atomic commit protocol and works in the following manner. Let's say we have two shards, the green shard and the gray shard, and a client who wants to send a transaction that requires attention from both the shards. So what in two-phase commit, what the client will first propose the transaction to all the involved shards here, both green and gray shards, and then wait for commitments from these relevant shards. These shards will locally validate the proposed transactions, and if the transaction is valid, they'll send a commit message along with the signature, and they'll locally log the potential state that this transaction can modify. Once the client collects all the commitments, it will send an execute message along with the proof saying that all the involved shards have agreed to execute this transaction. And once this shards receive this execute message, they will execute the transaction and they will send an acknowledgement message. So this is basically the classic two-phase commit protocol. And these are some issues, some minors and major. The minor issues are the client could be malicious, and then usually it is handled by replacing the client by another shard, where the client delegates his work to this client shard. There are other scalability issues, and that arises due to the fact that in two-phase commit, you have to wait for the slowest shard to respond before you can send an execute message. And this results in low throughput of cross-shard transaction and also longer latency. And in this work, we primarily address this problem, and we propose what we call Rivet. This is a new approach to execute cross-shard transactions in sharded blockchain. So here is an overview and model. So we consider partially synchronous network, and we also consider permission shard. Rivet has the following very high-level structure. We have a single reference shard that can tolerate up to third Byzantine failure. And we have multiple worker shards where each can tolerate up to half Byzantine failure. These shards are connected within themselves and also across shards. So both reference shard and worker shards has different purposes. Here, in Rivet, the reference shard works as a consensus engine, and it basically orders the worker shard blocks, and it also orders cross shard transactions. The worker shards, however, maintain state. They execute the transaction, both cross shard and intra shard transactions, and they periodically submit their state digest to the reference shard. It's important to note here that worker shard in Rivet do not run a consensus mechanism, and this is why we can tolerate up to half Byzantine failure even in a partially synchronous network. So here is our approach. So first, worker shards periodically commit their state in the reference chain, and this state commitment is equivalent to a promise that if the worker shards see a new cross shard transactions, they will execute the cross shard transaction on top of the latest committed state. And this is basically the crucial difference between two-phase commit, where shards commit their state only after seeing a cross shard transaction. But in Rivet, we proactively, each shard will proactively commit their latest state to the reference chain. And also, even if shards commit their state to the reference chain, they will locally optimistically execute intra-shard transaction with a hope that no cross-shard transaction will appear before they can commit the next state. We'll see Rivet in action now. So here we have two worker shard X1 and X2 and a reference shard X0. So each worker shard maintains their own blockchain, and they will submit their state ST0 and ST bar 0 to the reference chain. Let's say we have a client with three transactions, two intra-shard transaction TX1 and TX2, and a cross-shard transaction CTX1. The client will submit the intra-shard transaction to respective shards and the cross-shard transaction to the reference shard. The reference shard will first order the state commitments and also the cross-shard transactions. Once they are ordered in the reference shard, each worker shard will download the latest reference block, and they'll see that there is a cross-shard transaction that requires their attention, and then they will participate in a data exchange and using the proof using the latest committed state. And once they exchange the data, they will execute the cross-shard transactions on top of the latest committed state, and only after that they will execute the intra-shard transactions. And once they execute this intra-shard transaction, they will submit the new state digest in the reference shard, and the reference shard will order the new state digest, and this will continue to happen. So this is our approach at a very high level. And now I'll talk about how we evaluate our system. So the basic question in evaluating sharded system is how to shard accounts and how do we get a sharded trace where we have cross-shard transactions. The existing works considers a random partitioning where they randomly shard accounts to different shards and use a simulated transaction trace to evaluate their system. We consider a different approach where we look at Ethereum transaction history and access pattern and consider a more realistic sharding. So our approach is as follows. So we look at Ethereum accounts as a vertex of a graph where the edges between these vertex, we consider an edge if a transaction accesses any pair of edges. So here transaction 1 is accessing account A1 and A2. So we have an edge between them and we give an edge weight which is equivalent to the number of transactions accessing this account. So we have a transaction TX2 here that accesses account A4, A5, and A6. Here transaction 3 that accesses A4 and A6. So we complete this graph for approximately 10,000 Ethereum blocks and then create a balanced partitioning based on the edge weight and some other parameter like gas uses, and network bandwidth uses. So this is what a partition will look like, and this is a result on a 6 sharded system by using 10,000 Ethereum blocks. And here self edges are intra-shard transactions, and an edge between a pair of vertex is the fraction of cross-shard transactions. And in this example, we see only approximately 10% cross-shard transaction as opposed to approximately 90% cross-shard transaction in random partitioning. So we use this evaluation framework to evaluate our system. We also implement a two-phase commit baseline on top of quorum and evaluate it as follows. So we consider 6 worker shard and a reference shard. In two-phase commit, we consider a client shard in place of reference shard. We consider f equal to 3. That gives us number of 10 nodes in reference shard and 7 nodes in worker shard. We place them in a globally distributed fashion. And here's our result on confirmation latency of cross-shard transactions. As you can see, the confirmation latency in Rivet is much smaller than the confirmation latency in two-phase commit, which is the red bar here. And in particular, what we see is that confirmation latency of cross-shard transaction in Rivet is basically equivalent to the 1 block inter-arrival period of a worker shard. Whereas in two-phase commit, it's at least 2 block inter-arrival time of client shard. And that's why this is the difference. And it's important to note here that since we don't run a consensus within each worker shard, the intra-shard confirmation latency of Rivet will be higher than the intra-shard latency of two-phase commit. And in particular, the intra-shard confirmation latency in Rivet will be equivalent to the delay in the state commitment. And we see it's approximately like each worker shard almost commits their state immediately in the next available reference block. So we have a graph for that in our paper. Here is a result on throughput of cross-shard transactions, which we measure as follows. So for each reference shard block, we fire, let's say, 400 cross-shard transactions and observe how many of these cross-shard transactions are included in that reference block. And this, in some sense, captures the notion of logs, because in two-phase commit, accounts are locked for a longer durations. That's why we have lots of conflicting transactions, and we cannot include more than 50% cross-shard transactions. Whereas in two-phase in Rivet, we lock for shorter duration. That's why we have more higher throughput in terms of cross-shard transactions. So in summary, we propose Rivet, which is a new cross-shard transaction execution mechanism. We also have a new evaluation framework to evaluate sharded blockchain. In paper, we also talked about how to extend two-phase commit for smart contract and how we implement it on top of a Ethereum virtual machine. We also have proof of safety and liveness for Rivet. We also have more interesting finding on our evaluation framework. So this is the paper link, and thank you.